Okay, so I'm going to be talking about what I did during my 10 weeks here.
10 weeks long enough? Too long?
Just right.
Just right.
So I was working with MetPy the whole summer. MetPy is a library containing tools to read and visualize weather data. It has a unit support, which I found at first to be very annoying and kind of difficult to use, but I think it is a very useful tool, and after making it better, it'll be a little more useful. There's some plotting capabilities, such as UTs, station plots, water vapor imagery, etc. And there's also many calculations. So what exactly did I do all summer? When I came in here, I didn't have a set project that I wanted to work on. So instead of working on sort of a larger scale project, I did a bunch of smaller projects along the way. I first started out doing some calculations for MetPy. There's a list of calculations that we are looking to add to MetPy. A lot of them come from GEMPACK functions. So some of them that I added were Coriolis parameter, a conversion from pressure to height, equivalent potential temperature, saturation mixing ratio, and then attempted isobaric wind. I kind of wanted to do a more challenging function. Got the function working, but the numbers were not verifying. We had a little trouble with that, and after about a week or so of testing them against GEMPACK values and all that sort of stuff, we found out that the function required heights to go in x versus y, and ours were going in y versus x. So the order was switched. Feature solution to that, as Ryan pointed out, was to change the gradient function that's already within MetPy, so that way the user can sort of say which variable they want as the x and which one is the y. Then I went on to work on examples. We could always use more examples on the MetPy page and the notebook gallery. So some of them that I added were examples on wind, advection, meteogram, which I'm going to show some after this. I mainly use Siphon, which is a library to download data from the Thread server. So to start off, this is the first one that I made, 4-panel plot. I know we had another program like this, I guess, that someone else made. We kind of wanted to scale down the code a little bit, make it a little more simpler, using Siphon again to get the data. Also experimented a little with GridSpec, which is to control the layout. This was to try to get rid of the white space between the plot and the color bar beneath, and also lined up everything pretty well. GFS.
Resolution.
Quarter degree. This one is just the temperature advection plot. It was using the advection function that is already within MetPy. And then this one was vorticity advection. Yeah, Hurricane Frank. This one is sea surface temperatures. I kind of did this based off of one of the notebooks that Ryan put up. He had a similar type plot. I never really worked much with projections, so that's what got me to do this one. And this is just a meteogram type thing. Yes?
Oh, we're going to go meteorogram.
Meteorogram?
Yeah, that's lost it. I think by use of it, many of them seem stable. That's accurate. Sorry, I don't have to be geologist, but you know, the person that developed it meteorogram.
Okay, meteorogram.
It's not too language change. I think by default, meteorogram.
Anyways, won't say that word anymore. Moving on. This is also this is also based off of one of the examples that Ryan put up, so I decided to make one of my own. The top is temperature and dew point, and then wind speed, relative humidity, and then pressure at the bottom. Then I created a wind shear plot. So the green lines are sea level pressure. The yellow vectors are 850 millibar winds. The blue is 500 millibar winds, and then the pink is the vertical wind shear between the two. And my next example is also winds, but this is geostrophic and ageostrophic winds. So the red contours are 1,000 millibar geopotential height. The purple is the geostrophic wind, the green is the ageostrophic wind, and then the blue is the total wind. I sort of got this idea from something I did back at school. We were plotting data on GEMPAC, actually, data that we collected last summer, and we plotted different wind vectors together. We also did isobaric wind back at school, but again, the function did not come together this summer, so I couldn't include that on here, but I think it could be a useful tool, especially in MetPy, that sort of thing, to do wind vector.
Can you, I wasn't quite sure, you said you added, computed these things, you added these functions to MetPy library?
Well, the geostrophic wind function was already in MetPy. That's not one of the ones that I added. Isobaric wind, I was trying to add the function to MetPy, but that didn't work out like I explained before.
Some of these are, you know, thoughts to resetting things to the library in a couple of other cases you are trying to add to the library.
Yeah. Yeah.
Question. We're saying that we put together, so is it going to be added in the future?
Yeah, I hope so. Once I guess work on in the future the gradient function to sort of so you can specify like which x, what's x and what's y, so that way you won't have that problem with different sorts of data coming in different orders. With the with the isobaric wind function in particular.
Yeah, the red contours, red isolines of pressure?
1,000 millibar geopotential height.
So yes, pressure corresponds. And the purple is the geostrophic?
Yes.
Why is it perpendicular to pressure? Because of the surface. By definition, the surface is just friction.
No, geostrophic wind is from the gradient, not from the data. So,
Or to do some ratio, geostrophic winds are always parallel to the isolines. Yeah. This algorithm was in. All right, 10 more weeks. What was this? A roll of a 9.
I don't remember.
The geostrophic is something I wrote originally, and I'm going to take a guess. The same problem that did trying to validate the isobaric one against that probably cropped up here, where essentially it's the dimensions of the array. You need to take the x gradient and the y gradient, so you need to know which dimensions of the array are x and y. And you think you got reversed? I'm 95% sure because it's the same problem that I saw our wind dimensions. Why it's like, all right, we need to back up and make this easier so that people don't do that. Because you can throw wind data in there and it just ends up flipping the gradients.
everywhere you look, it's normal.
Yeah, you're right. It's
And that tells me that it's got flipped.
Yeah.
It's a good idea once it's...
Yeah.
So after I did the examples, I worked on galleries for the examples. I did this for both MetPy and the Jupyter Notebook Gallery. I think this is one of the things that was wanted, but there was no time recently to do it, so I decided to take a stab at it. And instead of having on the examples page to just have links, saying DT plot or station plot, it comes up with the actual images of the plots that are created in that notebook, a little more visual, and I think it's easier for the users to see the different types of projects you can do, and also, be able to be like, oh wow, that's cool, like, I'm going to click on that and see what it is. And so I'm just going to show you real quick what these look like. This is the MetPy example page. The only thing we need to work on a little more is some of the UT plots have white space around it. That's what's making it look a little funky. But you can just click right on the images and it brings up the page, and then you can also go to the notebook. And
And people are continually adding to that collection, the gallery, not really,
People being
well, the MetPy community
it's small. There are people using it. I'm working on trying to get people to contribute more. But yeah, and the examples keep growing, and people keep. Now with the images being up there, very nice addition. That it's easy to see what you can do and get inspired rather than read and wonder what does that look like.
Is the management structure in place for managing the composition, the categories, and titling? Is the framework there?
No. I mean, there's one gallery right now. We're still pretty early here. That's a good idea. Tagging, though. I think we have a volunteer. I don't know. It's general comment. There's no communication anywhere. I think it's Steve, when you said tag, you meant tag notebook with. This is a QT that does.
What if a person coming in from scratch trying to find something?
How many are there so far?
Yeah, at this point it's easy.
At this point it's easy.
Yeah,
right?
yeah. But there's some people that are contributing.
Oh. Yeah, there's 10,000.
Capacity,
I think I don't know how to without reinventing a lot of interactive tagging things. I think at some point we'd start dumping them into subreddits. Get you 90% of it.
so this is the more general Jupyter Notebook Gallery, so it's not MetPy specific. This is where a lot of the examples that I made are here now just because I use Siphon to get the data, so it's not MetPy specific. This one's a little more messy, this gallery. We didn't have time to fix it up, but same concept. You can click on the image and everything comes up. Then you click on the notebook link.
So only those data that are served through that server part of this collection.
Well, so for MetPy, it's all specific to MetPy and only what's in its collection of test data. So that the testing MetPy is not seeing external servers that help you out. For the notebook gallery, that's supposed to be examples, any kind of integrative across different tools types of examples. So the ones Kristen did, hit the red server and use MetPy and integrate multiple things. They could be, I'd love for that to be whatever our community, comes with the cool notebook to throw in there. Right now, it's very populated things I put on the blog. And then we have Kristen's examples. And we're going to be pushing hard trying to get people to send the notebooks over there. If anything relevant, we can MetPy, not MetPy, Siphon, whatever. Yeah, I think I can roll over this stuff.
And those would
Yeah. Yeah, I'm trying to keep MetPy because we run the examples to make sure they don't break. run them every time we commit. And it's good not to have those getting read or ACM or anything else. That's why one of the reasons that we created the notebook gallery wants to have a place to put these useful examples that aren't going to slow down definitely.
Okay, so the last thing I worked on for, I guess, the past 2 weeks was different kinds of widgets. This is my first time experimenting with them, so I kind of had to teach myself the basics. And I compared 2 different toolkits for the GUI programming. So I used tkinter and I used IPyWidgets. I found tkinter was easier to use for what I was doing. Things with more difficult layouts, this has easier tools to sort of manipulate the layouts. It has a place method, so you can specify where on the window you want to place each widget and the height and the width and that sort of thing. I also used IPyWidgets for 2 of the examples that I did. I thought this was good for more simple interactive features. I think this is because of lack of useful documentation on sort of harder examples on this, so I found it harder to teach myself the harder parts of IPyWidgets. So I'm going to show you 4 different examples. One is just a cosine sine function, and the GFS 12-hour forecast is using IPyWidgets, and then using tkinter is a wind calculation and thermodynamic calculation widget. So this is the cosine sine graph widget. This is sort of the first one that I worked on, just something basic to make sure that I could actually make it work. So basically what you can do is change the amplitude of these things, and you could also change the color of them. Moving on to the next one was a GFS widget.
If you go up to view, you can get rid of some of the toolbars.
Where's view?
You can view within your browser window under
Oh.
Tunnel. Oh, under Tunnel toolbar.
Okay, a little bit better. So I did this. You can change the variable on this. I also did relative humidity and wind speed.
Are those regenerating every time?
Yeah. And then you can move the time. Goes in 3-hour increments. And then you can also change the color map if you want to make it look pretty. This next thing was a thermodynamic calculation sort of widget. Basically, you can use the slider to change the temperature, the pressure, and the relative humidity, and you can get all these different kinds of calculations. And these are all using calculations that are already in MetPy.
So is this tkinter or?
Yeah, this is using tkinter.
Is that a pop-out dialog from within the notebook?
Yeah, yeah. Once you run the notebook, this pops up separately. Yeah, so basically you can change these, and you get all the calculations. How do I get underneath there? Okay. So then the other one was a basic using wind calculations. So you could change the wind speed, the wind direction, and the temperature, and you get out the U component, V component, and the wind chill. And these are also functions that are already within MetPy. Yeah, change that around. Cool to play with. Not mine. Okay, and lastly, I just wanted to say thank you for this opportunity. I think I came in here this summer thinking that I knew a lot and was really good at using Python everything, which didn't turn out to be the case, but I learned along the way, and I think I have a good amount of knowledge to bring back to school and use in the future. And a big thank you to Ryan for helping me out all summer with Python and MetPy. And that's it.
So in terms of lessons learned, what could be
well, I mean, I came in here only having had a Python class last semester in school. So definitely I learned a ton about especially like other libraries like Cartopy, which is used for mapping, and Siphon to download data, and more so using NetCDF files to read the data. I just think I broadened my knowledge a lot. It was a little frustrating. Certain things I didn't know. You know, Ryan would be like, "Oh, do you know how to do this?" And I'd be like, "No," and he'd have to tell me. But now I know so much more now, leaving here.
So, what domains is this appropriate for? What domains is not? Besides taking.
What?
Yeah. Appropriate for baking a cake. Oh. Are you talking about MetPy, or are you talking about her internship experience?
The MetPy. Yeah. So this is good for creating one-off exploratory stuff. Maybe there's some standard stuff you can use.
I mean,
useful in a classroom.
I think it would be useful in a classroom. I think it would have been useful if, when I took the class, you know, to have something like this, especially being a meteorology major, it would have been useful to have stuff like this. We kind of did similar type things with like plotting and stuff like that, but I think it would have been cool to have, you know, a QT plot and be able to plot all that up there and learn how to do that.
What about research?
I think it could be useful maybe in the future a little bit more once there's more stuff incorporated within MetPy. More calculations, maybe more plotting functions. I think it would be useful for researchers, you know, to plot up their data easily.
How do you feel how far away you are from being with JPEG?
I mean, yeah. Yeah, I mean, I think it'll take a little while longer to get to that extent, but I think it's going pretty well.
Once Python and MetPy catch up in years of single time, it's not the calculation that's the problem. It's the, since Genpack wraps all the data into its own file format and can, you know, standardize on a certain data model, that makes everything else a lot easier, and that's the part that we need to fill in there. And Genpack is still going to exist without a Genpack file, so so they're not adding a new encoder supporting new data types, they're saying EX is using the API to display data out. But Genpack can do all of it. Genpack and Python, yeah. Python and Genpack.
Any other questions?
I have one more. What could we have done to make it a richer experience for you? Other than more money.
Yeah.
I don't know. That's a tough question. I really liked working here. I really liked the environment. I thought everyone was always willing to help. I mean, especially Ryan. Every time I go and bother him, I'm like, you know, I don't know how to do this. I don't know how to do this. And he was always there to help me. And
I can leave the room if you want to rant.
No, I only have good things to say. I saw everyone was very helpful. You know, I felt comfortable going to Ryan for help, you know, multiple times a day, saying, you know, how do I do this? How do I do this? And he was always willing to help me. So I thought it was.
Well, one of the things past year interns that site, it looks like it didn't happen this year. The interns wanted more interaction with other technical staff, with staff, including their candidates here, so that they could learn more about Unidata beyond their project.
Yeah, I mean, I think I heard from, a couple people about like what they were doing. Yeah, lunchtime does that too. And I mean, I know like that was good enough for me. Like I heard a little bit about what was going on elsewhere, and that was really interesting to see what was going on throughout the whole company. But I also liked really focusing on Python and MetPy as well, because that's what I was really interested in, I guess.
And also, when you're doing this, you're exposed to
Is this a place you would want to come back and live?
Yeah, I really like it here. It's a good environment, good group of people.
some guys are packed and bunch of gone.
I mean, how could you not like working here?
I want to thank you for taking 10 weeks out of your life to come and spend with us.
It was a good experience. I enjoyed it. So. Boulder was nice.
Wonderful to have you.
Thank you. All right. You're up.
All right, so I'm also going to talk about what I did this summer, and I did some mapping stuff that I'm going to talk about, and also did all this in MetPy in Python. And I'm Alex Havers, by the way. We already talked about MetPy in the last talk, but the one thing that was missing that we, yeah, I got a picture of Ryan there.
Perennial.
Yeah. But the one thing that was missing that Ryan and I talked about was some mapping functionality. And that kind of included some interpolation functions that didn't exist in Python as of yet, and then maybe taking some of the functionality that's in Genpack and throwing it in MetPy. So the overall goal was to simplify our mapping meteorological data. And how to get about this is we have to have some way to make the functions that do gridding in Python easier for meteorologists. And for example, SciPy has this grid data function that already exists that has some interpolation functions in it. But the prerequisites for that are you need to know, okay, how do I take the coordinates from whatever data source I have and zip them and put them in a format to throw into this function? How do I get my observation values and throw them in this function and that sort of thing? And so you have a lot of extra code, a lot of extra things that can go wrong. So if we can simplify this for people that might not have as much experience in programming, that could always be a good thing. And yeah. So in Python, there's a way that you can take two arrays and kind of throw them into a single array. In this case, it would be you have x coordinates and y coordinates, so lat long values, and you want to throw them into one array. So in this case, SciPy grid data, you can't just throw x and y coordinates into it. You have to zip them and then throw them into the function. That might not be obvious to someone that doesn't have a lot of experience in Python. But if we could have a way that, okay, you just give us the coordinates, and in the back end, without you even caring or knowing what's going on, we can do these sort of things and throw them into functions like this. So that is a particular array where you take, your x and y range, and you need to turn them into this kind of 2D array that's friendly with plotting libraries. So it's like for each, so you have your columns and your rows, and you need to fill out the things in between. So there's a function in Python that allows you to do that, and that's kind of the prerequisite for plotting gridded data on a map. But I can talk about that in a second. So the next thing that we thought about doing was if we wanted to implement some interpolation functions that don't actually exist in Python, and some of the ones that Ryan thought would be good to do were Barnes, Cressman, and especially natural neighbor, which is something that I worked on a lot this summer. And then after we get all that done, can we create some sort of class that can kind of mimic some things that Genpack does and maybe allow some easier ways to map data. So the first thing we had to do was implement natural neighbor, and this was not a particularly easy task. And thanks, Julian, for letting us borrow the computational geometry books, learn more about computational geometry than I ever thought was possible. And unfortunately, we had to talk about some terms here. So basically, what natural neighbor is doing is it's creating a triangulation and using that triangulation and the attributes of that triangulation to kind of interpolate values at points that are kind of unknown at this point. So we have observations, and those observations are turned into triangulation. And then we have points within that triangulation that we kind of want to estimate what the value is. So the main kind of definitions that we need to know is if we have a triangle, the circumcircle of that triangle is where all 3 points lie on the edge of that circle. And then the circumcenter of a triangle is just the center of that circumcircle. So you see it kind of gets a little complicated to keep track of. And the circumradius is just the radius of the circumcircle that's created by that triangle. And then the Delaunay triangulation is where you have a bunch of observation points, so lat long values, and you want to turn that into a triangulation where each one of those values is not within the circumradius or the circumcircle of any triangle. So it kind of lies on the edge of these circumcircles. And then for natural neighbor, you take all of those together and you say for a given grid point, the triangle is a natural neighbor if that grid point lies within the circumcircle of that triangle. So it takes it a step past some of the more simple triangulation interpolations where they just look at, say, one triangle. This takes the natural neighborhood associated with the grid point. And got some pseudocode. If you're not a visual learner, maybe this will help explain it. If you're a visual learner, just hang on for a second. So we have a bunch of grid points in the United States, for example, and for each grid point, we need to find its natural neighbors, and then the natural neighbor triangles, we need to find the kind of outside of all those triangles, the edges, and then for each edge, you're looking at the point behind it and the point in front of it, and you're creating these new triangles which then you calculate the circumcenters of those triangles, and these create these little polygons, and you take the area of those polygons, and eventually when you find all of the polygons that are associated with all of your edges and your vertices, you then estimate your interpolation value by weighting those areas. So if you have a smaller area, it's going to have a smaller weight according to the overall area of all these polygons that create. And so I did an example to kind of, because we had to do some testing on this to make sure things were working. And I did a really simple example where I threw a bunch of points on here. So the coordinates don't really matter. These are just random points. So this is what the triangulation would look like for these points. And what I did for the temperature was just say like x squared. So as you go up to the right on your x-axis, your values are going to get higher. Then I divided by 1,000 to kind of make it reasonable numbers. And so you have this triangulation, and say you want to estimate a value for your grid points here. So you have grid 0 and grid 1. And so the natural neighbors for grid 0 are the triangles associated with the red circles. And then the natural neighbors for grid 1 are the triangles associated with the blue circles. So the circles represent the circles that are created by those triangles. So this is kind of the prerequisite, the pre-processing that we need to do to find, for each grid point, say, okay, what is my natural neighborhood? And then from that point, then we can do some calculations on our polygons. So then the process goes, I'll use my laser pointer. The process goes, if we want to, we're right now at our edge here, so our value is, this is the value we're looking to weight. So we go to, if we're going to go counterclockwise here, we say, okay, the two vertices here is our behind vertices. So we create a triangle from this vertice and this vertice and then our grid point, and then create a circumcenter, calculate the circumcenter here, and then we go to the point forward from this and the grid point and create a circumcenter here. And then each triangle that 3 is associated with, we take that circumcenter, so these points here, and then we create our polygon. And so we do this for every vertice in this natural neighborhood, and then create these polygons here. And so I kind of calculate the areas here and printed them out. So we have this area is 70, don't really care about what unit that is, but just look at the relative value. So you have 70, 60, and then this area is very large, so 448. So we would suspect that this value here, 1.156, is going to have a pretty big weight in this calculation for this grid point, which kind of makes sense because it's very close. So I also did a kind of another visualization. So if we step through each grid point, so this is actually from a larger example I'm going to show you in a second. So we have our current grid point here, which is squared, and these are all of the calculations that we need to do for that grid point and all of our weights. And then as we step through, we go to the next one and the next one, and we see that our neighborhood changes. And you can have really complicated sort of amalgamations of polygons here where you have to calculate your areas and then look at the relative area to find your contribution. So for example, for this point, you're going to have for the value 13.9, just think of that as temperature, you're going to have, that's going to contribute 2% to your overall value, and then you just, more or less, you just times 0.02 by 13.9, do that for every one of these, sum that up, and then you get your interpolation value for this. So that's what you're doing for natural neighbor. And so once we completed that, we wanted to test this against the existing interpolation functions that exist in SciPy. So there's linear, there's nearest, and there's cubic. Then we also found a C wrapper for this package called NCAR NatGrid, which actually has a natural neighbor function built into it, but it's in C. There's some weird sort of licensing issues. There's actually some discussion on some of the some threads, I think, associated with Unidata in the past. But it was just something that wasn't very convenient or even possible for us to use in MetPy. So we had to rewrite natural neighbor, and then we compare it to that one that seems to be kind of a more established natural neighbor approach. Yes. Mm-hmm.
What's going on in Oregon? Yeah.
There was just, so this is just a station, random station plots around the United States, and I think this is something that Ryan created in January, and I'm assuming that you just said, okay, stop everything at this certain longitude and
$7.
Yeah, you can see the value as a linear feature.
Yeah. So there's a bounding box around here, so maybe 120 west or something, and it's just I just use this because it already existed in MetPy, and you might as well reuse things so without adding more test data to the package. And so each one of these stations has a bunch of variables, and I just chose air temperature. That's kind of an easy thing to start out with. So we have minimum -24, maximum 26, and actually cut it off a little in that range. You'll see in some of the examples I show, I didn't go all the way to the end of those ranges. And what we want to do is we want to see, okay, how does our algorithm stack up as far as times goes, and we'll see that. So processing time, so you say, okay, for the United States, if we want to say, okay, let's see how long it takes for 50 kilometer grids, 150 kilometer grids, and see how it stacks up to existing approaches. And probably the more important thing is that the visualization of the function, the interpolation function, is on the same level as the other approaches and is nearly identical to the existing natural neighbor. So first, the timing, and we expected this because MetPy is pure Python. That's it. We didn't use any tricks. I'm going to talk about some things that we tried to speed it up in a little bit, but we didn't include in the pull request. But just so no one's fooled, this is logarithmic scale, so it's much slower than this. Yeah, or 2 words, I think. But that's, you talk yourself into that, like at least I did. Okay, that's okay, because this is a good first start. It's just in Python. These other approaches use Cython, which I'll talk about in a second, even C and C++ on the back end. So those are going to be faster than Python. That's just all there is to it. And but it's nice that we have a proof of concept, and I'll show you that it actually looks exactly the same as the natural neighbor that already exists. So it's good to have this in the package now. And we see that what's promising is we see that the shape of this is very similar to the existing natural neighbor. So that kind of gives at least me some idea that we're going in the right direction, and there isn't some sort of other things going on. It's just, okay, this is just Python slowing us down. So I did some examples here, and so this is Python nearest, and this is what you would expect from a nearest neighbor interpolation. You have a lot of kind of segmented areas over the United States. Nearest neighbor can be faster in some situations, but obviously there's cases where it's just not going to look as good as the other approaches. Some ways that you can get around this is if you use some sort of Gaussian smoother or something that might make it look better. But in this case, it's probably not as useful, at least on this scale. There's cubic, and we have some issues, and we have maybe some weird data, kind of higher temperatures than usual up in Canada here. I just kept all the data just because it's kind of nice to work with, real world data and see how it looks. We get to linear. This is also SciPy. It gets a little better in Canada. Very smooth interpolation surface. And this is the natural neighbor from NCAR. And this is one that exists at wrapper. And then this is natural neighbor in MetPy. It's not a mistake. It looks exactly the same. Yes, so I was very happy about this. There is a nice little Easter egg. Sure. I disagree. Yeah, I mean, so yeah, that's the question. Is it worth the effort? And I was convinced that it was, and I do think it is. This might not be the best example to show showcase it, but this is the example that we have.
It would be validated against observation, right?
Yep.
That's how you would know if it's better or not better. The thing to do is to take a small subset of the data and withhold it from the interpolation, and then compute the discrepancies.
Or to take an analytic field. So you know what you can compute. It's been a long time with this problem.
What is nice, what I think will make it worthwhile, even if you don't really care about the differences between linear and natural neighbors, there were a bunch of helper functions that were created along the way, and just having those in the package might pay off in the future if someone needs to do some things that are related to this. But
They ask you on a national scale, what I'm assuming like on a smaller scale. I think the large scale root functions There's other computers like scale processes, just scale level.
And also, the thing about natural neighbors is if you're not doing anything to compensate for your data density and your actual geometry of observations. So if you have one on one side of your grid point, you have 4 observations, and one on the other. Linear doesn't do that at all. It needs to do the data, do the distance weighted stuff, whereas natural neighbor accounts for that actual arrangement of the observations.
And then also what's nice is we're going to talk about some inverse distance weighting functions as well as to kind of mimics that, I would say, without having to deal with the certain parameters, kind of universal parameters. So in the inverse distance, you have a universal search radius, for example. In this case, I feel this is a more natural area of influence.
Like I mentioned, you're saying how do you decide how far out you go?
So what we do is we have this. So we say if a grid point is within the circumcircle of a triangle, we include that triangle in the natural neighborhood. Otherwise, we see like for this grid or whatever, we see that these triangles have circumcircles that are too far away from the grid, so we wouldn't consider these to be our natural neighbors. So that's our kind of the way that we decide to cut off. Or I don't decide that, that's the way the algorithm decides.
Depending on the density of the observation. But you only get the ones that geometrically surround the grid point. You don't take extra points in it.
And then we saw something kind of odd in the existing natural neighbor. So you'll see in this case, you'd kind of expect that that this subset should be pretty much if you just cut off. So what I did was I said, give me all of the observations below this line, maybe the Mason-Dixon line, I don't know. But yeah, that was an accident. Okay.
No.
Yeah. So you'd expect that this would just kind of, if you just cut this image off above that line, you expect it to be the same thing below, but that isn't the case. And this is NCAR's net grid. So this is the existing wrapper. But then we look at yeah, and then we look at MetPy, and I think it's much better as far as the stretching.
What's the reason for the stretching along the ladder?
When I found that, I was like, why is this? I'm not sure if it's something that's speeding up, making assumptions about something, or maybe you say like runs of grids maybe have the same value or something. I don't know. It's really odd because.
Did you try this for different?
I did not. This one is Albers equal area, but I didn't. The thing was the grids are exactly the same in this. I'm not sure how much this is used. Yeah.
I don't think anyone's really supporting that anymore.
So the thing is, the underlying grid of this is exactly the same. The only difference is the northern United States is just masked in this case. And when I say mask, it's not plotting those data because there are no data to plot.
Do you try using this as a subset?
I tried a bunch of different things I didn't show. It seems like it's more sensitive to having things squashed latitudinally than having things squashed longitudinally. But it was just it was odd, and it was one of those things I wasn't sure what was really going on, but we decided that that wasn't really a functionality that we wanted to emulate. So
It's not unique to a given set of points. You have several lines from applications to a set of points. You wind up with real narrow, long triangles. The influence of the point is
Yes.
yeah.
I don't know what they're using it inside the net grid for triangulation.
Right.
Yeah, they don't put that out.
Did you compute any objective measures of the accuracy of the map?
I mean, the only thing that we kind of did was compare it to the existing one. And it seems like on this orientation, it's similar, or very similar. And when I did the subset to compare it, it was pretty dissimilar. So initially, what I was doing was looking at just difference. So doing like, yeah, so just doing raster map.
When you say similar, is that imputed? How do you do similarity, or is it just judging?
Judging. And I did kind of a more quantitative test where I actually did a raster difference. So the grids are exactly the same, and you'd expect if the algorithm was exactly the same or had the same output, that your difference between the two grids would be very small, and that was the case. So that I did not do any sort of error metrics or that sort of thing. Because I think one of the reasons why maybe we didn't do that was because what are we calculating against? You know, what I did do was I showed that picture of the books and the pieces of paper. I did the calculation by hand. So basically all I did was use the helper functions that I created in MetPy and said, okay, I need to find the circumcenter or a circumcenter radius or something like that. And I knew where the points were. So I would then write that on the piece of paper and say like, okay, I did this calculation by hand, what is the value, should the value be? And then compare that to the output from the automated function, and it was the same. So according to the algorithm, in those few cases that I tested, they were the same. And then we also do, so those testing I did by hand were also then transferred to the testing suite that we have that I added to MetPy. So if anything is changed in the algorithm, we know that it's going to be different than what I verified by hand. You know, any suggestions on, you know, how to make this, people believe this more are welcome. I mean,
I think the algorithm is written correctly. The next step, like the AMS, supposed to do the thrown in away for the comparison, just to see how they do it for the analytic field and the set of scattered observations.
yeah.
So I've noticed a lot of effects. So curious how much of this you do that, how much of the effect you So up in Canada, on the left side, I mean, this used to be, so you showed a couple of examples, like warm spots in Canada, which you can see a pretty big difference in how it's treated up in wet. And I noticed when I reproject gridded data, I get this effect, British Columbia, Quebec, like 5 degrees latitude where it's like knocked out. And that seems to be caused by mesh handling the top left and top right corner. So how much of this is due to the color mesh? How much of it is due to
I didn't do that. The first thing that we kind of just jumped towards was something that he discussed. So on the edge, you can have really long triangles, and sometimes that kind of does some weird stuff. But that would be something to investigate. If P-color mesh is what's creating that, that would be something that we should definitely look into.
If you have the base map the exact same as the projection, which the mesh handles it as P coordinates X, Y, and
So what maybe I could do is, I'm going to look at some examples in the Jupyter Notebook, and maybe I'll just plot the basic grid. Is that the kind of issue? So what you're thinking is if I have my values in an array and I'm passing it to P-color mesh, that's going to make things weird. But if I have just the basic array without any mapping information, it wouldn't have that weird stuff going on in Canada? Okay.
Will you actually base that or part? Well, I don't think Alex has part of doing any reprojection of the heat color. Your grid's in alpha area, right?
Mm-hmm.
So there's no heat color at that point, and then just drawing squares or blocks. So there's zero effect from the plotting. It's all interpolation. I agree. Northern Canada, I don't think there's a cold spot. You know, that's not right along the edge. I'm not sure why that's going on.
And you know, another thing is I included all the data, and it's possible that, so if you have discontinuities in your data that are kind of unnatural, like say like temperature that's just way off, maybe that also contributes as well. But okay, then the next step we're going to do some inverse distance weighting, and these were much more straightforward, and there were a lot of good, helpful kind of walkthroughs on the Unidata pages. And so these weights are just based on how far your points are from your grid point that you're trying to estimate a value for, and usually you just say, okay, I only want to consider points within a certain search radius. And so for both Barnes and Cressman, they're doing basically the same thing, just different approaches to it. And this is I believe this is a map from Unidata's page where they show an example of mapping these sorts of things. And so this is the Cressman, and one decision that we made was if we don't have a minimum number of neighbors within our search radius, we're just not going to plot those. We're not going to calculate those data. And this is the same data set as before, and it's just station plots with, and this is temperature. I'm not sure where exactly the station plots.
A set of METARs come across the red back in January.
Okay. But yeah, you see some of the inherent issues with the inverse distance weighting, kind of these circular sort of features here. Yes. And you can get rid of those if you do your search. So this is changing your search radius. So things get a little smoother. And so I think one good thing about inverse distance weighting, if you have a large enough search radius, things are pretty smooth, especially on this scale. But sometimes you don't want that sort of smoothing. So if we increase our minimum neighbors up to 5, we see that we run out of, so you have to have 5 neighbors within 100 kilometers of your grid cell. And we see the areas that have kind of more dense are the ones that are getting plotted. So, this isn't necessarily, you wouldn't suggest someone to do this, but just showing that if you change the minimum number of neighbors that are required to do the calculation, you're going to get different results.
These are one pass, right?
The as far as I know, the Cressman does just one pass, and it's that, I didn't see the algorithm for Cressman where you do 2 passes, but okay. So for both Barnes and Cressman, I did 1 pass. But in the future, you could add multiple passes, which basically takes the error that you build up between what you expect and your output and throws that into your next pass to make it a little better, it seems. So here's our Barnes, doing similar things to a Cressman. I'm just throwing this in an example. And then what's nice is you can then take multiple interpolation. You can interpolate multiple sort of variables. In this case, I have sea level pressure, our wind barbs, and our temperatures, and you can plot this on a map. So these wind barbs are not model output or anything. They're actually interpolated from our station. So it's kind of neat if you want to do that sort of thing. And then, so now we have at least kind of the basic back-end functionality, added some interpolation, added some wrappers to existing interpolation functions. So now let's do an interface, and basically the interface, what we want to do is if a user has, as long as they have coordinates and they have some sort of variable that they want to plot, we should be able to take care of most of the rest. And that's done through having default values and also giving the user the ability to set these values. So you pass in your column values with your observation variable, and it should return a grid back and grid, mesh grid fishnet objects that you should just be able to throw in the Cartify without having to really think too much about it. And I'll show you the actual interface in a second. And what's nice, and something that Ryan has underlined since day one, is that we have 98% test coverage on this interface package. So in the future, you know, things can, if something changes and breaks, we'll definitely know. So I'm going to show you these, at least briefly show you the package. Hopefully it loads. So this was recent. This is my branch, but is recently included in MetPy's master branch, I think just yesterday, 5. So we have, I was talking about these helper functions, so kind of the byproducts of creating the natural neighbor. And so we have functions for triangle area, you know, distance, that sort of thing. Not that there aren't other packages out there that would probably have better functions than this, but they exist if we want to add some more things that need to use these sort of triangle functions. For points, some basic things like find all your points within a radius, and then the really important stuff that's helping the user to not have to think as much about plotting data is let's generate our grid coordinates based on our data and our data range, and then some other helpers here. So let's find the boundary of our coordinates in our observations, and you can also find the coordinates of all your grid points. That's something that's very helpful when we're doing our interpolation. And this is where all of our interpolation functions live. So we have natural neighbor, and then we actually have a function for a point, natural neighbor for a point, which is called by natural neighbor, and all of our inverse distance weighting functions. And then the actual user interface, what people are going to mostly work with, is this function, so interpolate. So we have a bunch of options here. We pass in our x, y, and z values. We don't have 3D capabilities yet. That might be something that's added in the future. A bunch of default values that might work for, you know, synoptic scale mapping of these sorts of things. So even if users don't necessarily know how to, you know, what is my, I guess they have to supply the search radius, but they don't know what kind of interpolation type they need to use or the resolution. We give them some values here that are the default values, and they pretty much only have to care about their x, y, and observation values. So then it's just, it goes through and says, okay, what's my interpolation type? And then does the interpolation and then returns our grids and our values. And then an actual example of this. So all these notebooks are on the MetPy page if you ever want to check out or do any of this stuff. So this stuff is just kind of the setup that's not really, it's important but not really important to showing the functionality here. So I'll just do MetPy natural neighbor. So if we want to create an interpolation with MetPy's natural neighbor, all we have to do is pass in our x, y, and temperature values, our temperature arrays, say natural neighbor, and then give the resolution for a grid. And then this gives us back our mesh grid and our image. And then you can plot this using Cartify.
Out of curiosity, how long does it take to run that cell?
This cell, so for 75-kilometer resolution, I think it was in the order somewhere around 5 seconds.
Oh, that's bad. But if you wanted something higher resolution?
Yeah, it gets pretty bad. 50 kilometers is 12 seconds, and then it just increases from there. I showed you after, I think 50 and above, I showed you some examples. So it's not too bad in that range, but once you get down to 10 kilometers or something, unfortunately, it takes quite a bit of time, and I'll talk about some of the ways that we might be able to do that in the future. But yeah, as of now, using this to plot data with 10 kilometer grids is going to take a while, unfortunately. And I also have a warning. Actually, I've built in a warning that says, like, if you go below 10 kilometer grid here, it says, like, oh, this is going to take a while. And another choice that we might do in the future is it's not necessarily obvious. Okay, it's 75,000. Okay, that's meters. What if the user wanted to say 75 kilometers? We talked about maybe including units in this with some of the built-in units functionality, but that's going to be something that's included in the future. But yeah, I have a bunch of all these examples on the MetPy page if you want to look at them. I also have the SLP. So to do this, just more steps in interpolation and greater plots here.
You have a notebook basically laying out the nearest natural neighbor, like the early graphs you had for displayed.
Actually, yeah, we do. We weren't sure. They're included for now, but so, for example, I did a verification notebook just to make sure things are working correctly, and explain some things. Okay, if I have this point here, what triangle does it belong to, or what triangles are its natural neighbors, and just showing some stuff like that. I have a more in-depth notebook that we did not include, but do this one. Okay, yeah, so all of these, yeah. So I have this one. So if you ever want to step through, you ever found yourself? I don't know if that's ever going to happen, but so yeah, these are the steps that I did to go through to verify. Okay, are my proportions and weights correct? And what is my by hand interpolation value, and then what is the value that's coming from my natural neighbor point? And see that they're very, very similar, and these are kind of just literally human errors from my simplifying and rounding. And so now that we have the interface, something that I've been working the last 2 weeks was actually create some sort of mapping class. And this was kind of the idea we had from the beginning, but had to take a step back because we wanted to do some of the back-end stuff first. But if we have some GEMPACK, let's take some, yeah. And if we have, this is actually an example from the documentation page, not MetPy. This is the GEMPACK documentation page. So, okay, we have some variables here that we can set. Okay, can we do this in Python? And the answer is kind of. This traitlets class allows you to have these configuration files. So a user could have a configuration file in their local version of MetPy, and they'll say, okay, I want to have my bounding box be these values. I want to plot these certain features on my map, and then kind of the details about this is we have our MetPy map object with, I'll show you the properties in a second, so we set those properties, and so when you load the notebook, all these properties are going to be thrown into your MetPy map object. And so the user won't even have to set these in the notebook, they could just create their own little configuration file and read it in, which is kind of nice. So this is kind of our, or at least my version of maybe similar to GEMPACK.
So did you do a mapping of all of the GEMPACK functions? This is not a GEMPACK NTS file. It's like an NTS file, but it's going to. But you're correct. So that's what it's going to drive to the file. but it's no
You're not,
longer.
Not at that point.
no.
That's something that we talked about. It would be cool. I mean,
Well,
if you could say like read in that sort of thing and translate it to something that Python can understand, that would be kind of interesting. But this is our first step to it, and it's in pure Python in this case. So the syntax is actually just exactly like Python.
Python 5.
Yeah, it's Python 5. And what's nice is you can actually call certain libraries in your configuration file. So if I want to set my projection, this is how I do it. And then we get to our class that is actually going to, so you can have a configuration file or you don't have to have it. What's nice is in this package called Traitlets is you can actually set properties. And what's nice is you can actually enforce data types in Python, which is somewhat unusual. If kind of the knee-jerk reaction of Python is you can necessarily enforce these sorts of things, but Traitlets lets you do that. So you can set your default values, and you can, if the default values are kind of complicated, you can actually have functions that set default values. And what's really nice is you can have this observe decorator, which then it's basically in waiting for the event where one of these properties is changing. So if, for example, the bounding box value changes, this will trigger this function to then run, which in this case it's to redraw our map here. So if bounding box changes, let's redraw our map to then be updated to the bounding box. And I'll show you an example of that. Have it up. Yeah. So in this case, we're just importing this class that's then inheriting from traitlets. So it has all the stuff that a traitlet class should have. And we see that in this notebook example, I read in the configuration file and just plot it, or just write out what the data that are in there. So this is what we expect to go on. And all you have to do is then instantiate your MetPy map object. And just based on your configuration files, you see that nothing really is going on here, setting bounding box or anything like that. And we see that some events were triggered, and then we have a map that's based on our configuration values. So this is kind of nice for reproducibility and kind of ease for a user just to set their configuration files and draw the map, and it plots. You can also do some things like let's change the properties, and we see that we aren't doing anything here to say, okay, update the map now. That's all done in the background, and it's triggered by changing the bounding box. And so now we've changed our bounding box, shift a little more to the west, and we display our map, and now we see that our map has shifted to the west. And we take a closer look at our bounding box object here. We see that it's a dictionary, and then we actually require that within that dictionary we have east, west, north, and south. So if a user doesn't supply those, we kind of throw an error. If they aren't floats, we also throw an error. And I show you that example here. So if we set our bounding box dictionary, we see that if we have a string of -120, I don't know why you do that, but the traitlets will yell at you and say, okay, this has to be a float, not a string. And then we can also, I did some widget stuff, so we can actually plug this into our widgets. Just have to run this. Apologize, I thought this was already running, but apparently someone's going to fail on that one. But then we can plug this into our widgets like we saw in the last presentation. Maybe. That was weird.
You put an error in.
Yeah, so the error is going to stop it from running everything, but then I ran everything below that point. Yeah. Yeah, I apologize. I thought I had this running beforehand, so please bear with me. So it's going to break there. Okay, so we have some things that we can change. So let's turn off the oceans. Make this a little smaller. We can change our features on and off. And this stuff is just, these events are just changing the properties in our MetPy map object, which is then triggering, redrawing the map in the background, and then once we decide then to plot the map, then we can plot those changes. And what's nice is there's a nice little function that says let's not update until we actually take our finger off the clicker. Yeah. So, yeah, so in this case we can change our wind direction. I don't know why you'd want to do that, but. And then kind of the more obvious one is we can change our bounding box. So that's kind of something I've done the last 2 weeks. It's not really polished, but this could be something that's added in the future to MetPy. So we're not done with 4, unfortunately. I won't go into this example, but this is just some Python stuff. So for the basics, we want to get things faster. So for some functions, we're actually able to decrease the runtime, and so kind of 4 microseconds to nanoseconds here, which is always a good thing. And these functions are just basic calculations, and it seems, unfortunately, for the more complicated ones that it's going to take a little more time. I kind of ran out of time in this case, but hopefully in the future we'll have some Python functionality that will then have these on the same order of magnitude of how long some of the more established interpolation functions are taking. And we see this little
Very small. It's a little bit slow.
So anyway, summary. Sorry if it took longer than wanted, but created some wrappers for existing functions and also implemented some interpolations that were needed that did not exist in Python before this. Then the interface, and what's really nice is the very high 98% test coverage. So in the future, if we change anything and it still works, we're going to be very confident that this sort of thing, that the function is working correctly. Kind of a proof of concept of this Genpack-like stuff moving forward. Maybe that's the direction that this sort of thing will take, maybe not. And also investigated if Python can speed things up. And unfortunately, it wasn't very straightforward, but maybe in the future, someone like Ryan maybe can figure it out. And then I'd like to mirror what Kristen said. Thanks, everyone. The lunchtime stuff was really great for camaraderie. If anyone hasn't experienced that, then you need to try that out. And also thanks to Ryan. Every single day we had questions, and he was more than happy to help us out. He lent me one of his books on Python, and then everyone else that we had questions to, from ranging from scientific to administrative. Everyone is very happy to help out. So thanks to everyone. And that is the end of the presentation.
All about how this could be parallelized. I know this is Python, but
I believe it's incredibly parallelizable because it's doing a calculation for each grid. And if you're able to then, and then it comes to the point, like, the questions asked before, is it worth it? And, it might be interesting, but the other problem is we can't necessarily assume that the users are going to have multiple cores available to them. I think potentially the main audience for this is going to be researchers or students that have just maybe a basic laptop or desktop. But definitely, if we had access to a bunch of cores, you could simultaneously do these calculations on every grid in the United States at the same time if you wanted. And then that kind of gets to the, yeah, it'd be really cool. That'd be really cool to do. But then it kind of gets away from the potentially the vision that you have for the actual interpolation algorithm.
And you look at ESMI at all, or ESMF framework, state-of-the-art interpolation, and they do all their interpolation at the Fortran level. They have Python interfaces for it.
Something that we talked about was that any sort of code that needs to be compiled is going to be kind of a pain for the package management and kind of really kind of endangering Ryan's sanity in some cases. But I did not look at that package
On to sort of solve some of those.
But if it tells you anything, I think people beg me to rewrite ESMF because it's a word English law.
Yeah, but I mean, you're never going to be able to reproduce.
I'm not saying, all I'm saying is, I'm not looking into things that are English law. That's, all my point is, people have asked me to do this already, so that tells me stay away unless we really need it. And I know they do cool things in terms of mass conservation and things like that.
Yeah.
But it's a different problem.
Their objectives are different. They're trying to do reprinting a couple models.
Right, and that's reprinting. That's not taking the scattered odds.
Right, yeah, their objectives are.
Yeah.
I have a much more common question. Is Python a dog when it comes to competition?
Raw Python, the way that one is, yes. Basic Python.
I'm actually surprised to hear that, given its proliferation in really high-performance computing circuits with high-energy physics and cosmology.
Well, there are a lot of
all of the micro computations that are done in Python.
It's the end of the pipeline.
Well,
Visualization. It's the end of your pipeline, of your workflow for the visualization part.
Let's step back a second. If you use NumPy right, you can get perfect good performance, but that's running in C. So what the NumPy package does, it provides an array object that the whole point is to avoid looping in Python, and it drops all your calculations to C, and then it's not slow. The problem is with the interpolation routine that Alex has been working with, all those individual triangles, you're not really dumping it into C and doing looping in C, you're doing a lot of Python level looping, and that's where Python ends up slow.
Yeah. It's always the best, or at least fastest when C.
Fortran better than.
Yeah, you're not going to write your hard-performing computing model.
How does this performance compare to Java's early performance improving so much with this and whatever?
This is a good time to bring up the guild.
No, we're going to need to lead for a group of people who don't do Python.
But then you're limited by what the global interpreter law, which fundamentally limits parallelization in Python. Is that correct?
That's correct. I just wasn't thinking the audience was very.
Okay, well,
The way that we could
forget the word guild.
No, but I mean, I am happy to get into the discussion of Python performance. But if,
Let's
you know,
talk about
there we go.
the way you could address that,
I want to talk about that later.
Happy to. I would love.
the way you could address that in Python as it is a multi-processing package. And it exists. I've used it before and it does speed things up. It's a little clunkier than maybe what you used in other languages, but there's some built-in functionality that allows you to use multiple processors. But
Remember the target should be looking for the processing. Rapid processing.
that's earlier in the summer we were joking about that, how we could use something like Haiku to speed it up. But
There is. PyOpenCL. Really go down that route.
Are those robust? Are those mature?
Anything OpenCL keep it looks mature.
Plus you get into the data dependency problem that you were trying to avoid all along. Right?
Okay, I'm going to ask you the same three questions.
You're ready for them now.
You remember the three questions? By the way, thanks so much for the presentation. Part of the problem, so we appreciate what you've done. One question I had was, what could we be doing better for future in terms of giving them much better, richer experience in the program in terms of how they spend their time experience?
Well, I hate to be a broken record, but I completely agree. It was a great experience. You came in confident in your abilities, and about halfway through you were not confident, and then you built up maybe 1% of that confidence. But it's good because the one thing I found was you need to know what you don't know. It's kind of weird to say, but I thought the experience was great. The only thing I would add is being able to have 2 monitors. That's the only thing. But no, but seriously, it was a really great experience, and I can't thank Ryan enough.
would have given you one of his. I would have been happy to consider it.
But that's an easier price. Monitors are pretty cheap these days, and it's something that easily grabs.
I guess I'm half
Take
joking.
notes,
I'm half joking about the monitors because I could have asked them for.
Was your computing environment?
Yes.
Did you feel like we doubted the screen thing? We had enough.
Yeah, and what was actually nice about this is we talked about this is that potentially having like the best computer possible might have hindered this because maybe we wouldn't have tried to make it more efficient. But we definitely got into the weeds of getting the most we could out of the algorithm, and it helps. If we were running this on a supercomputer or something, maybe we wouldn't have thought to delete a few lines or combine these lines. But yeah, the computing was adequate. I was happy.
What was the reading infrastructure you had access to?
Basically just the desktop, which was adequate. I mean, it had enough RAM, had enough processing speed. It was fine. The issues that I ran into were mostly algorithm related. So.
Who's your development environment?
PyCharm. Yep. Yeah. And just to simplify things, we actually use this program called GitHub for Windows, and sometimes use the Git command line, but that GitHub for Windows seemed to work. And then we had used PyCharm and the Anaconda distribution and using environments and stuff. So if we wanted to test on our computer, Ryan has infrastructure set up for testing that tests almost every version of Python. But locally, I used environments, so set up a Python 2 environment to make sure things are working. And that's all done in Anaconda.
What are your plans going forward?
My plans going forward are to try to finish my dissertation as quickly as possible. And I have some teaching responsibilities in the coming year. And then after that, it's either going into academia, a research position, or something like that. And I'm very happy for this opportunity here because I think it also, having this on my resume and having Unidata be a card name, and that's something that's easily recognizable. So if I wanted to go into some sort of more maybe scientific programming area, it's an invaluable experience to have instead of just being an instructor or research assistant.
Thank you again.